This is a video lecture for physics, for General Physics 2, for Monday, April 6th. And this is the final chapter of the semester. We're covering chapter 25 on electromagnetic induction and electromagnetic waves. So we're almost to the end. You guys have been faithful and you've endured a lot of hardship, which I am so sorry for. But we're close to the end, and this chapter 25 will not be on exam number 3, but will be on the final exam. So you will get a homework assignment for this that will be due the last week of school. And I do apologize that I'm piling on the homework and everything, but we'll be able to have this on the final exam, and the final exam will be online, obviously. Just to give you an idea of schedule, today we will have video lecture for chapter 25. Wednesday, April 6th, we will have video lecture for April 8th, we will have video lecture on chapter 25, and I'll finish up the chapter then. Friday is Good Friday, so there's no class. The following Monday, which is April 13th, we will, I'll collect your homework and I'll review for exam 3. Wednesday, April 15th, you'll complete exam 3. And then Friday, April 17th, we will review for the final exam. And I will have a review sheet for the final exam, so you'll know which problems we're going to do. There will be one problem per chapter, starting with chapter 18. Is that right? We do, yeah. We either started with 17 or 18. It's been so long I can't remember. But we'll start out with light waves, and then we will have one problem per chapter. Okay, your final exam I will post sometime the week of finals, and I will give you a time period. I don't have the final exam schedule in front of me right now, but I will give you a time period in which that you complete the final exam. It will be a 2-hour test, so you have 2 hours to complete the exam, and I'll tell you a little bit more about format as we get closer to the final. Okay, but anyhow, here in our last chapter, we're going to talk about induced currents. And it just so happens that when a charged object moves through an electrical or a magnetic field, that can induce a current as long as it's continuing to move. We'll talk about motional electromotive force and how electromotive force is generated in moving through magnetic fields. We'll tie that to magnetic flux and how magnetic flux works with electromagnetic radiation, okay, and then we'll talk about Faraday's law. Faraday's law relates electricity and magnetism directly. And then we'll talk about induced magnetic fields and electromagnetic fields and electromagnetic waves. We'll talk about the properties of electromagnetic waves. This is how energy is propagated through space. Talk about the photon model of electromagnetic waves. Talk about the electromagnetic spectrum. And this is not your homework. I will not be giving you homework until Wednesday, and that assignment will be due on Friday, the 17th of April. So please disregard this slide. Okay, so it turns out that if you have current that is moving through a coil up here, okay, where's my arrow? Never find my arrow. Okay, there it is. So if you have current moving here, if you just if you close the switch and all of a sudden you initiate current, the instant that you close the switch, then that will create a magnetic field here. Okay, that magnetic field will interact with this coil, and that will create electricity just as soon as that switch is being closed. So you'll get a small deflection if you're measuring current here through this amp meter, then you'll get a small deflection just as the switch is closed, but then it will go back to 0. Okay. If you have a magnet that's moving, so you have a moving magnetic field, a changing magnetic field, that will also create a displacement. It's shown in the negative direction. It can be negative or positive. And then if you have a fixed magnet, but you push or pull the coil through the magnetic field, so if this is moving, the actual coil itself is moving, then that will also cause an electric displacement away from 0. Okay, so in Faraday's law, if there is a current in a coil of wire, if and only if the magnetic field passing through the coil is changing. So if you can change the magnetic field by closing a switch, by pushing or pulling a magnet, or by pushing or pulling a coil through a magnet, then you're changing the magnetic field that's seen through the coil, and that will induce electrical current. That type of current is called induced current. So what will happen is if we have an electric field going, or a magnetic field, excuse me, going into the page, and I take a conductor that has charge on it, and I move it in a velocity v through the magnetic field, then that charge carrier is going to experience a force of magnitude, force using the right-hand rule with the electric field, with the magnetic field. If it's a positive charge, it will move upward using the right-hand rule. If it's a negative charge, it will move downward with the right-hand rule. Okay. Now this resulting charge separation, where the positive charges go to the top and the negative charges go to the bottom, creates an electron motive force. Okay, so you'll have an upward magnetic force on the positive charges, and you'll have a downward electrical force on the negative charges, and that downward electrical force is associated with the electric field that builds up in this conductor, and those are equal and opposite. So as you're pulling this conductor through this magnetic field, then with a velocity, then the magnetic field in theory is changing. The force due to the magnetic field is offset by the force due to the electric field. So the force of the magnetic field is going to be equal to the charge times the velocity times the magnetic field. That will equal to the force times the electric field, which is equal to the charge times the electric field. The electric field is equal to the velocity then times the magnetic field, or the electromotive force is equal to the velocity times the length of the conductor times the magnetic field. Okay, so you can calculate what your electron motive force is just by knowing the velocity that you're pulling something through a magnetic field, the length of that object, and then the intensity of the magnetic field. Okay, so here's our first learning check, our example. How much potential voltage would develop across a 1 kilometer tether that was traveling through Earth's magnetic field at a speed of 8 kilometers per second. Okay, so go to our document camera here. You can see that. And so we know the electron force is equal to our velocity times our magnetic field. Okay, L is length. That looks like a dividing, like I'm dividing through, but that is a V, an L, and a B for magnetic field. Okay, we have a tether of length 1 kilometer. It is moving at a velocity of 8 kilometers per second. In our magnetic field, this is just the magnetic field of the Earth. We can get this directly from the textbook. Tesla. Okay, so once you have that, then you can plug in numbers. And we want to bear in mind that this is 1,000 meters, and this velocity is 8,000 meters per second. Okay, so then E is equal to 8,000 meters per second. L is 10,000 meters, and the magnetic field of the Earth is 5 times 10 to the negative 6 Tesla. Okay, that will give an answer in volts. Don't worry about the units at this particular point in time. So we go ahead and do our calculation. And we take 8,000 times 1,000 times 5 times 10 to the negative 5th, and that gives us 400 volts. So a tether, say if we were establishing a tether on the space station, and it was moving through space in orbit at a speed of 8 kilometers per second, and the tether was 1,000 meters long, then it could develop a substantial voltage. Okay. So chemical reactions in batteries cause chemical EMF. Okay, this is the potential difference of the electric field going from positive to negative in a battery, and that's delta V battery. Magnetic forces separate the charges and cause potential difference between the ends, and this is called motional electromotive force. Okay, emotional electromotive force means that the conductor has to be moving. Okay, so this conducting object here has to move through this magnetic field. It has to be changing, so it feels a change in the magnetic field as it's moving with this velocity v, and our change in voltage is just equal to the velocity times the length of the conductor times the magnetic field. So if somehow I had a conductor here, I have a wire, and then I have a sliding conductor that can slide along the wire and complete the circuit, and I pull it along at a velocity v, and the wire has a resistance R, then whatever my electromotive force is that's associated with this magnetic field, the length of the conductor, and the velocity v, then whatever that voltage is there, I divide it by my resistance, and then that will give me my current. Okay, so I is equal to my electromotive force divided by my resistance. That's just current is equal to the battery power divided by the resistance. So that's also equal to velocity times the length of the conductor, and that's an L, not an I, times the strength of the magnetic field going into the page divided by resistance. So induced current moves through the wire. Okay, there's a magnetic force that's associated with the current that is opposite the motion, and then there's a force pull, and that force of the pull must maintain a constant speed of this conductor. If it maintains a constant speed of the conductor, then the current will also become constant. So in other words, the pulling force and the magnetic force have to balance out. The magnetic force you will have to oppose with your pulling force, and if those two balance, then you will be moving at a constant speed. Okay, so the force of the pull is equal to the magnetic force. Okay, now, because there's current, there will be power dissipated in this rail or this length here that's associated with the dissipation of power. Okay, so that this will create a resistance. The pulling takes work, and that pulling will induce power into the system. So just the force of pulling over a length is work. Work is force times the length that it acts through, so that will be Newton meters. And then that will impart power depending on the velocity at which you're moving through. So the force of the pull is going to be equal to the velocity times the length, L squared, times the magnetic field squared divided by the resistance. Okay. Now let's say you're generating electricity. So you have a permanent magnet and you have a generator coil here. And if you look at the electron motive force of this coil, which is running through and gaining power from this magnet, then, and you look at the electron motive force that is being created here, then that as a function of time is going to go from a positive electron motive force to zero, down to a negative electron motive force, up to zero, back to a positive, and then you'll have a sinusoidal wave. Okay, so your electron motive force will actually change polarity. It'll be positive, then negative, then positive, then negative, and it'll follow a sinusoidal function. So then if we take our loop, this is just a loop of coil here, and we're just seeing it from the side. And let's say it's the axis of the loop is parallel to the field, so theta between the field and the loop is 0. Okay. If the axis is tipped by theta, then the flux going through is little b cosine theta, okay? Where b is this length of your diameter of your loop, okay? So the magnetic flux is then changed. You'll have less magnetic flow going through, and that will change the magnetic field. Okay, so if my axis of this is a square loop, and the field is coming out towards you, then my axis is parallel to the field, then the maximum magnetic field is coming through, or I have maximum magnetic flux. But then if I bend it, okay, in the magnetic field, instead of having B, then I have B cosine theta, and the loop is tipped by the angle theta, then I'll have less magnetic field, so I'll actually have a flux of magnetic field going through. So the magnetic flux at any angle theta is just your effective area. This is the area of your loop, times your magnetic field, or A, your area of your loop, times B, your magnetic field, times cosine theta. Okay, magnetic flux is measured in Webers, and this is an important phenomenon because you have magnetic flux going through as a current loop is rotating around, then the magnetic flux is changing, and a Weber is equal to a Tesla times meters squared. Okay, so let's say I have a loop of wire. Here's my loop of wire here, A, and it's tipped at an angle theta, okay, to a uniform magnetic field B. Okay, so my magnetic field is B. The maximum flux occurs at an angle of theta equals 0. Okay, so if I were to able to take theta and make it equal to 0, then the maximum, I'd have the maximum magnetic flux. Okay, so we want to know what angle will give us half of the maximum magnetic flux. Okay, so what we would have to find out is where does cosine theta equal to 1/2. Okay, so if we have theta equals 30 degrees, just go back and I can show you the slide. It's AB cosine theta. So if theta equals 30 degrees, just take out your calculator, make sure you're on degrees. That would give you a cosine theta of 0.866. Okay, so that's not half. If theta equals 45 degrees, that gives you cosine theta of 0.707, which is not half. If theta equals 60 degrees, that gives you cosine theta as 0.5, and that would give you half the magnetic flux. So the answer is C, theta equals 60 degrees. And once theta equals 60 degrees, then the magnetic flux will be cut down by 1/2. Okay, now this is where we introduced Lenz's law. In Lenz's law, there's an induced current in a closed conducting loop if and if, only if, the magnetic flux through the loop is changing. The direction of the induced current is such that the induced magnetic field opposes the change in the flux. Okay. So if I have a magnet at rest, it creates a downward flux through the coil, okay, and the current with that magnet at rest equals 0. If I move the magnet downward, that increases the downward flux through the coil. Then the loop generates an upward pointing field that opposes this change. And a counterclockwise current is needed to induce the upward pointing magnetic field. Okay, so if we take our current, and that's our thumb, then in order to oppose that field, the field would have to go upward, so our fingers curl up through the coil, and that shows that the current must be counterclockwise. Okay, and so just by that opposition, just by moving that magnet, you would get an opposing magnetic flux, and that would create a current in the coil or the wire that is positive. Okay, so the flux has to change. The magnetic flux through the loop has to be changing in order to create current. So the magnetic field through the loop changes in the previous slide just by moving the magnet. It either increases or decreases the flux, or this can happen through the loop changing in area or by the loop changing in angle. or the loop moving into and out of a magnetic field. Okay, so when you use Lenzs Law, you determine the direction of the applied magnetic field. The field must pass through the loop. You determine how the flux is changing. Is it increasing, decreasing, or staying the same? Then you determine the direction of the induced magnetic field that opposes the change in flux. So if you have increasing flux, the induced magnetic field points opposite to the applied magnetic field. If you have decreasing flux, the induced magnetic field points in the same direction. And if you have a steady flux, meaning that it's not changing, then there's no induced magnetic field and you'll get no current. So once you know if your magnetic flux is opposing the applied magnetic field or it's in the same direction of the magnetic field, then you can use the right-hand rule to determine the direction of the induced current. Okay, so we have a long conductor and it's carrying a current and it runs next to a loop of wire. The current of wire in the wire varies as in this graph. Okay, and we want to know which segment of the graph corresponds to the largest induced current in the loop. Okay, so we have a long conductor, it's carrying current, and it's next to a loop. So we'd expect the biggest flux to be point E, because your current is changing most dramatically in point E. In point A, the current is going up. B also, C it's pretty steady, D it's going down, but the most dramatic slope that you have, regardless of whether it's positive or negative, is E. So you will have a greater induced current. Whether it's positive or negative will tell you what direction it's going to move in the loop. Okay. So next we have a magnetic field going through a loop of wire. The magnetic field is going into the page. And if we say that the magnitude of the magnetic field is increasing, then what can we say about the current in the loop? Okay, well, first of all, we know that if the magnetic field into the page is increasing, then our opposing magnetic field is actually going to be moving in the opposite direction. So our opposing magnetic field is moving out towards us. Okay, so we use our right-hand rule, and if it's moving out towards us, okay, we just wrap around and have our fingers moving out towards us in the coil, then that means that the current is going to be moving counterclockwise. Okay, so B is the correct answer. If the current moved into the page, or I'm sorry, the magnetic field moved into the page, we would be wrapping in and we'd be going in a clockwise direction. But our opposing magnetic field, this is going to oppose the magnetic flux going into the page, is coming out of the page, and so your fingers move out, and that gives you a counterclockwise current. Okay, so try that with the right-hand rule. Now, if the magnitude of the magnetic field is decreasing, then our opposing magnetic field is also going to go into the page. And if it goes into the page, then we will have a clockwise current. So in this instance, the loop has a clockwise current, or you need to answer A. So take some time, work through those. The first answer for this previous problem was B, because the magnetic field is increasing. And the second problem is A, because the magnetic field is decreasing. Okay, let's try this one. Let's say we have a battery and a loop of wire and a switch that makes a circuit. We have a second loop of wire below it, and just before the switch is closed, what can we say about the current in the lower loop? Okay, so in order to get current in this loop, you have to close the switch. So before the switch is closed, there would be no current in this loop. It would not exert a magnetic field on the second loop. The second loop would not have an opposing magnetic field. And so because of this, there would be no current in this lower loop. So the loop below has no current. So C would be the answer. Okay. So if we want to devise what our electron motive force is induced by a current loop, if the magnetic flux of the loop is changing, then the flux change is delta phi, that is the Greek letter phi or phi, and the flux changes over time, delta t, then the magnitude of the electron motive force is just delta phi over delta t, and the direction of the EMF such to drive an induced current is the direction given by Lenz's law. Okay, so first we use Lenz's law to determine the direction of the induced current. Then we use a mathematic representation of what our flux is over time, our magnetic flux over time is, that's delta phi over delta t. And then if we have an N coil or N turn coil, say we have multiple turns in our coil, then that will give us a higher value of E, our electron motive force. And then the size of our induced current, I, is just E divided by the resistance in the coil. Okay, so let's say we have our 10 centimeter loop, diameter loop in 3 different magnetic fields. The loop's resistance is 0.1 ohms, and for each situation, determine the magnitude and direction of the induced current. Okay. So in the first example, our magnetic field is increasing by 0.5 Tesla per second. So that's our magnetic flux. That's delta V or delta phi over delta T. That would just be the magnetic field moving through that area. Okay. And we can take what our magnetic change in magnetic field is, and we can use that to calculate what our magnetic flux is. Okay, so if we take the first instance where our current is increasing, or our magnetic field is increasing by 0.5 Tesla per second, coming out at us, we have a loop. Okay. Our diameter of our loop is 10 centimeters. Okay. Our area of our loop is equal to pi times 5 centimeters squared is equal to pi times 0.05 meters quantity squared. Okay. Okay. And our flux is equal to A times our magnetic field, okay, and delta flux over delta prime is going to be equal to our area times our change in magnetic field per time. So that's 0.5 Teslas per second. So our change in flux then is equal to negative 0.0003 Tesla meter squared. Okay, so we know that previously though, that is equal to our electron motive force. So our electron motive force then is equal to 0.003 volts. Okay. My resistance, 2.1 ohms. Okay. And my current is equal to electron motive force divided by resistance. So that would be 0.0393 amps. Sorry, 0.0393 amps. Okay, so that's for the first instance. Now if we go back to the second instance, oh, and by the way, if that's increasing at 0.5 Tesla per second here, then our magnetic field, our opposing magnetic field, would be going down into the page. And if we use the right-hand rule and it's going down into the page, then our current would be moving clockwise, and it would be moving at a magnitude of 0.0393 amps. Now, if it's decreasing at 0.5 Tesla per second, and it's going into the page, then our opposing current would also be going into the page. So again, for B, we would be moving clockwise. Okay, use the right-hand rule. Because your magnetic flux is decreasing, then the opposing magnetic flux is going to go in the same direction. So you use your right-hand rule. So the current is moving clockwise. Again, none of the parameters have changed. So you don't need to recalculate. So it would be 0.0393 amps. And it would be going clockwise just as it was in A. Now, in C, your current loop is actually pointing in the same direction. Your current is going in the same direction as your magnetic field. So whenever your current is going in the same direction of your magnetic field, then your magnetic flux through that loop is going to be zero. So if your magnetic flux through the loop is zero, it doesn't matter if your magnetic field is changing or not, it makes no difference, then the current in the loop would be zero. Okay. So let's do one example, then we'll call it good for this lecture. So let's say we have a coil and it's used to make TEMS, transcranial magnetic field stimulation, for a TEMS device, producing a magnetic field that increases from 0 Tesla to 2.5 Tesla in a time of 200 microseconds. Suppose this field extends throughout the entire head. Estimate the size of the brain and calculate the induced EMF in a loop around the outside of the brain. Okay, so I'm going to make some wild assumptions here. I don't know how big a brain is, so we'll just go ahead and switch over to the document camera. The coil, they're not given how many loops are in the coil, so we're just going to assume that n equals 1, so we'll have 1 loop. Move my phone. So we have a brain. We're just going to look from the top of it. Okay, and I'm just going to so let's just 10 centimeters and focus. Kind of focus. Okay. Then we have our change in field is equal to 2.5 Tesla minus 0 Tesla over time, and that is 200 microseconds. Okay, our area is equal to 0.05 meters squared times pi. That's a little bit better. So we calculate our area, 0.05 squared times pi is 0.0785 meters squared. Our change in magnetic field over time is equal to 2.5 Tesla divided by 200 times 10 to the 6 seconds. That's just 200 microseconds. So that gives me 1,250 Tesla per second. If I want to know my change in flux over time, then I just take my change in magnetic field over time, multiply by area. So that is 12,500 Tesla per second. Keeping off the page again, times by area, 0.0785 meters squared. And that will equal 98.125 Tesla meter squared per second, which is also equal to 98.125 volts. Okay, so that's my voltage in my tens machine. Okay, so let's go back to the original problem statement. So the induced EMF in a loop around the outside of the brain then would be 98.125 volts. Okay. Okay, for now, I think we're at slide 22. So we're about halfway through the chapter. I'll end it at that for the video lecture for today, Monday, April 6th. And then we'll have another video lecture on Wednesday. Do not forget that tomorrow, Tuesday, is lab, so we will have a video lab, and I will post the handout on Moodle before the video lab is posted, so you'll be able to fill in the blanks.